Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we have introduced the basic concepts for the quantifiers, both their syntax and their semantics. In this section, we discuss the valid rules of inference concerning statements with quantifiers in deduction. There are 4 rules: universal instantiation, universal generalization, existential instantiation, existential generalization. Below, we explain each rule in detail, together with examples. The rule of universal instantiation reads, from a universal statement, deduce a specific instance. It means that given a premise for all x px, we may replace x with any term c in the domain of discourse and deduce the proposition pc. We also remind the audience that the rule of universal instantiation can be applied multiple times for multiple instances. Let the set of all real numbers be the domain of discourse, and consider the following arguments discussed at the beginning of predicate logic. Every positive real number is greater than -1. 1 is a positive real number. Therefore, 1 is greater than -1. The universal premise can be written as, for all real numbers x, if x is greater than 0, then x is greater than -1. Using the rule of universal instantiation, we substitute x with the real number 1 and obtain the true proposition. If 1 is greater than 0, then 1 is greater than -1. Together with the premise that 1 is greater than 0, it implies that 1 is greater than -1 by modus ponens. Recall that we are not able to complete this deduction using only the rules of propositional logic. But now, our argument is complete and valid, thanks to the predicates, the quantifiers, and the rule of universal instantiation. The rule of existential instantiation suggests that from a true existential statement, deduce the truth of the formula for some fresh element c in the domain of discourse. It is really important to note that typically we don't know who is c precisely or what other properties c might satisfy. Any reasoning that follows should assume nothing about c beyond the fact that p of c is true. For example, consider the existential statement, there exists a black swan. From this, we are allowed to claim that a swan, to which we assign a fresh name, Mochi, is a black swan. Is Mochi male or female? Does Mochi live in Australia or Austria? We have no idea at all. The only thing we can say is that Mochi is a black swan, and the name Mochi has not appeared before in the context of our deduction process. The previous 2 rules are called the rules of instantiation, as they allow us to start from a quantified statement and arrive at a statement about a specific instance. The next 2 rules work in the opposite way. They begin with a statement about an instance and generalize it to a quantified statement. These are called the rules of generalization. The rule of universal generalization reads, from an arbitrary case, deduce the universal statement. It means that given the premise PC is always true for any arbitrary term c in the domain of discourse, we may conclude that the universal statement for all x, px, is true. When writing proofs, we often begin by letting c be an arbitrary element, and from there, work with that instance. Note that we should not assume any extra property for c, apart from its being in the domain or subdomain of discourse. This guarantees that the choice of c does not lose generality, so the argument for c can be applied verbatim to any element in the domain or the specified subdomain, thus ensuring the validity of the universal statement. For example, let the set of positive integers be our domain of discourse. We can pick an arbitrary positive integer, say n, and show that 4n is a composite number. Since the choice of n is arbitrary and fully general, the conclusion drawn from this instance is sufficient for us to establish the validity of the universal statement. Finally, the rule of existential generalization permits us to deduce the validity of the existential statement from that of any specific instance. As people always say, seeing is believing. For example, consider the following equation. We may easily verify that when we replace x by 1 on both hand sides, the equation holds. In other words, 1 is a real solution for this equation. From there, we can conclude that the equation has at least a solution, as we have already found a solution. Now you have learned the basic rules of inference for statements involving quantifiers. Since these are ubiquitous across all areas of undergraduate mathematics, we will provide more detailed explanations with examples in the next section.
신라 텐세